So this is the 17th session in the subject of digital communications, and we are going to study Emery signaling in this particular session. Now, Emery signaling we have also touched upon in one of our earlier lectures, but we are going to study more details about Emery signaling. So let us start. So what we'll do is we'll quickly revise what we already know and then take the study forward. For example, we know that if our number contains a single digit, that is either 0 or 1, then you require just two waveforms. 0 is represented by S1t and 1 is represented by S2t. So 0 is mapped to S1t and 1 is mapped to S2t, so that easy transmission is possible. So this is basically what we call as binary signaling. But suppose in a digital world we have more than one digit. Suppose we have two digits. So you may have combinations like 0, 0, 0, 1, 1, 1, 1, 0 and so on. In that case you will have four possible combinations. So you will require four waveforms to represent this. So let us look at this. So 0, 0 will be coded by S1t, 0, 1 will be coded by S2t, 1, 0 is coded by S3t, and 1, 1 is coded by S4t. So this is called as quaternary signaling. In general, if you have k digits in a word, then the number of waveforms m is equal to 2 raised to k. Note that when k is equal to 1, you got 2 waveforms. When k is equal to 2, you got 4. If k is equal to 3, then you will require 8 waveforms in order to represent the binary word. Okay. Now, we have already studied how S1t, S2t, S3t, S4t can be generated. And in one simple example, we had said that you can simply use a pulse of differing amplitude. So S1t will be a pulse of certain finite duration of one amplitude. S2t could have a larger amplitude, S3 further, and so on. That is one way of doing it. Now in this session what we are going to do is to study a more general method of generating S1t, S2t, and that method relies on signals which are called as orthonormal signals. Using orthonormal signals, we will be generating S1t, S2t, etc., the signaling waveforms. So what we are going to do now is to define what orthonormal functions are. Okay. So orthonormal waveforms. First of all, note that they are designated typically by using the letter phi. So you have phi 1t, phi 2t, phi 3t, phi 4t, etc. right up to phi nt. So the number of orthonormal waveforms in general are going to be n. They could be as small as 2 only. It could be phi 1 and phi 2 only. Okay. Now, these are also called as basis functions. Now, what are the properties of these waveforms? They are explained by a couple of examples, a couple of equations rather. So if you multiply any two, so suppose I multiply phi it and phi jt, where I is equal to j, then I'll get 1. What it means is that if I take phi 1t and multiply by phi 1t itself, I is equal to j, both are equal to 1. So I'll get phi 1t squared, and when I integrate I'll get unit. So this normal term corresponds to that. And the same goes for any other function. That is, suppose I take phi 2t square and integrate it over the symbol time period, I'll get 1, and for all other functions as well. But if I is not equal to j, for example, if I multiply phi 1 with phi 2 and then integrate, then I'll always get 0. So it doesn't matter whether I take phi 1 into phi 2 or I take phi 2 into phi 3 or phi 1 into phi 4 and so on. They are all orthogonal to one another. So orthogonality means that if you take the product and integrate over the symbol time period, you will always get 0. So because of these two conditions which are satisfied by these functions, they are called as orthonormal waveforms. Now the next question you might ask is, how do you generate this? Now there are a number of ways of doing this. I'll just tell you one simple method of generating these. If you consider two waveforms, one A sin omega t, another A cos omega t. So it can be shown, and later on in one of our lectures we'll show that sine and cos under certain constraints are orthogonal to one another, and they will be orthonormal if you appropriately adjust the value of A. Okay, so this tells you what orthonormal waveforms are, and this is one example of possible orthonormal waveforms. Now we have said that we use orthonormal waveforms in order to generate our signaling waveforms, that is S1t, S2t and so on. So how do we generate them? So let us see the equation for that. Suppose I want to generate S1t using the orthonormal waveforms. Then what I do, I select S11, which is a coefficient of F1t, select S12 as the coefficient of Phi2t, and so on. How to select this, we'll comment on that a little later. But right now let us assume that these orthonormal functions are given to us, they are known, and these coefficients are known. If the coefficients are known and if the orthonormal functions are known, then S1t key is generated simply by adding these terms. Similarly, S2t can be generated. So here now note the change in the suffix here. This is S21 is the coefficient of Phi1t when S2t is being generated. S11 is the coefficient of Phi1t when S1t is being generated, and so on. So S22, Phi2t plus etc., assuming capital N number of orthonormal functions. In general, SIT will be SI1 Phi1t plus SI2 Phi2t plus etc. SIN Phi nt. Okay. So this particular equation will be useful at the transmitter where S1t is to be generated. So it will generate S1t, S2t, etc. by utilizing S11, these coefficients, and by utilizing the orthonormal functions. We'll see a block diagram soon. But these equations are useful at the transmitter in order to generate the signaling waveforms. This is in these equations written in a compact form. SIT will be equal to sigma of j equal to 1 to n Sij phi j t. Okay. Now what about finding the coefficients? So suppose S1t is given to me. So finding the coefficients will be an operation which will be required at the receiver, and we'll soon see why that is so. But suppose S1t is available to me and I want to find out S11. So what I do, I multiply this entire equation by Phi1t. So this will become S1t into Phi1t, and then integrate both sides. So the left hand side will become, here I have written it on the right side. So the left hand side in this equation becomes the right hand side of this equation, which is 0 to t S1t Phi1t. Remember what we have done? We have multiplied both sides by Phi1t and then integrated. Now the right hand side here, S11 is a constant. Now when you multiply this by Phi1t, this will become Phi1 squared t. So Phi1 squared t integrated will be equal to S11. Now when you multiply this term by Phi1t and then integrate, the product of Phi1 and Phi2 integrated over symbol is going to be 0. That is the case for all the remaining terms. That is why this right hand side has got only one term, which is S11. Here it is written on the left hand side. I hope this is clear. What you have to do is to multiply throughout by Phi1t and integrate over the symbol time period, and you will get S11. Similarly, if you want to obtain S12, what you have to do is to multiply throughout by Phi2t and then integrate over the symbol time period. So you can get all your equations. So in general, Sij will be integral 0 to t Sit phi j t dt, and here I is equal to 1, 2, 3 up to m. Remember, m denotes the number of signaling waveforms and n denotes the number of orthonormal functions. The two need not be same. Indeed, we'll see an example where we may have just two orthonormal functions and we can generate a large number of signaling waveform using that. Okay. So this S1t, which is a function of time, can be represented by a collection of all these coefficients. So Si, so it becomes a vector which is a set of all the coefficients. We'll see how it is shown geometrically soon, but understand that S1t is one definition of the signal in the time domain, but it can also be defined in another domain by using only the coefficients here. Okay. Now, in order to see this geometric representation in a simple fashion, what we'll do is we'll consider only two orthonormal functions and generate the signaling waveforms. So S1t is equal to S11 phi1t plus S12 phi2t. Then S2t is equal to S21 phi1t plus S22 phi2t. Similarly S3t, S4t, and in general SIT is given by this. Now we want to see how to represent this S1t in a geometric fashion. In fact, we'll be using S11. So what we'll do is we'll use two axes, X and Y. On the X we'll plot the coefficient of phi1t, and on the Y axis we'll plot the coefficient of phi2t. So various vectors can be drawn for the corresponding signaling waveforms. So let us do that. As I said, X-axis contains the coefficients of phi1t and Y-axis contains the coefficients of phi2t. So a couple of examples are shown here. So S1 is a vector here. Now this has a coefficient along coefficient of phi1t along the X-axis, and that is S11. Remember, this is representing S1t. So its coefficient along the phi2t is S12. So this is your resultant vector or a resultant phasor. So S1t is represented in the phasor form or the vector form by S1. Similarly, S2t is represented by its vector form or phasor form by looking at its coefficient of phi1t along the x-axis, which is S21, and its coefficient along the y-axis, coefficient of phi2t along the y-axis. So this is S22. All right. So similarly, S3, S4, 5, S5, etc. can be drawn. What we will now do is to look at one very specific example in which the various coefficients are numerically specified, and then see how the constellation diagram looks like. This is called as a constellation simply by looking at these collection of points. Just to make it look similar to a constellation, I have just drawn stars here. Basically, it's a point at this point and a point at this point. Okay, so let us take a specific example. S1t is 1 into phi1t plus 1 into phi2t. This means S11 is equal to 1 and S12 is also equal to 1. Then S2t is equal to 1 into phi1t. This means S21 is 1, but S22 is minus 1. Similarly, S31 is minus 1, S32 is minus 1. And finally, S4t is this, S41 is minus 1 and S42 is plus 1. Okay, so if you make a plot of this, you got 4 points. S1 with coefficients of 1, 1, S2 with coefficient of 1 and minus 1, S3 with coefficient of minus 1 and minus 1, and S4 with a coefficient of minus 1 and plus 1. And note that each point corresponds to a particular value, the digital word. So 0, 0, 0, 1, 1, 1, 1, 0. Incidentally, note that as you go from here to here, 0, 0, 0, 1, there is only 1 bit change here. And as you go from 0, 1 to 1, 1, there is 1 bit change. So if a noise occurs and by mistake, although S2 S2T was transmitted and you decode that S3T was transmitted, there will be only 1 bit error. You can see that this 0, 0 and 1, 1 have a distance of 2, Hamming distance of 2. In other words, 2 bits are different, but the distance is much larger. So this error is less likely to occur. So it is the difference between these constellation points that will decide the noise performance of the signaling design. Okay. So in this case, we have 4 points because we had 4 waveforms. Now, if you want to build a more efficient system, understand the advantage of coding a digital word with number of bits is that when you decode, let's say S1T simultaneously, 2 bits are decoded. So it's more efficient. Similarly, if you code 3 bits, then you will require 8 waveforms. So you will have 8 constellation points. But then the distance will become smaller and the noise performance will be poorer. So you will find that you will gain something, but you lose something also. So let me show that constellation to you. 0, 0, 0 is represented by this point 0, 0, 1, and in general you have 8 waveforms: S1, S2, S3, S4, S5, S6, S7. These are all vectors corresponding to the time domain signals S1T, S2T, and so on. So you can see now the advantage is that when you detect say S1, you automatically detect that 3 bits were transmitted which were 0, 0, 0. So that's an advantage. But now the distance between these two, geometric distance between these two neighboring points has reduced, so the noise performance will reduce. Okay. Now let us see how the signal generation is done. So let's say digital input. For example, suppose we are coding a doublet 0, 0, 0, 1, etc. So if digital input is 0, 0, then this table lookup will generate this output as S11 and this as S12. So S11 is multiplied by phi 1t, then S12 is multiplied by phi 2t, they are added and you generate the signaling waveform. So signal generation is quite simple. All you require is a table lookup. So for example, if this was 0, 1, then appropriate coefficients will be generated and the appropriate signaling waveforms will be finally generated. Okay. What about the detection at the receiving end? So let's say the received signal is xt is equal to SIT. This is what you would have received if there was no noise. So if SIT was transmitted, you will receive SIT if there is no noise. But since there is some noise, which WT represents wide Gaussian noise, so the received signal is not strictly same as SIT, but WT gets added to that. So we call that as XT. Now what we do here, remember the equations by which we were finding out the coefficients, those equations are now useful here. So what you do, the received signal is multiplied by phi 1t, then integrated and you get x1. This is the first coefficient. You multiply it by phi 2t, you get the second coefficient. Okay. Now ideally, for example, if S1t was transmitted and there was no noise, then you will find that this is exactly equal to S11 and this is exactly equal to S12. So you can just check what were the received coefficients and take your decision. We'll see soon how we take the decision, but the point is that these x1 and x2 that you obtain are coefficients and they'll be exactly equal to the coefficients which were used at the transmitter if there was no noise. But because there is a noise, these x1 and x2 will not exactly match the coefficients which were used at the transmitter. So then what do we do? The answer comes by looking at the constellation diagram. So we will use that example in which 4 signaling waveforms were used and these are the 4 constellation points. Now as I said, if there was no noise at all and if S1 was transmitted, X1 will be exactly equal to plus 1, that is S11, and X2 will be exactly equal to plus 1, that is S12. But because of the noise, you find X1 could be smaller than this, so and X2 also could be smaller than this or greater than this. In short, the received vector will not match with any of the vectors which was transmitted. So how do you take the decision? So it is simple now. One way of checking which signal was sent by checking the quadrant. So you find out if this is lying in the first quadrant, then you conclude that S1 was sent and therefore 0, 0 was the original waveform. If it was in this quadrant, then you conclude that S2 was sent and therefore the original signal was 0, 1 and so on. So simply by finding out, in short, you will find if both x1 and x2 are positive, then this is the quadrant. If x1 is positive and x2 is negative, this is the quadrant. So this is one simple way of detecting which waveform was transmitted. Okay. Now this particular method looks okay here, but if the number of constellation points increase, then you may have to use a more sophisticated method. So in that case, what you do is you use what is called as a Euclidean distances. So let's look at this. This is S1, this is S2. In general, there can be many, but right now, just to illustrate how to find the Euclidean distance between the received vector and the transmitted vector. So suppose D1 is the difference between the received vector and S1. Then notice this is D1. So how do we find this? This is S11, this is X1. So D1 squared will be this perpendicular squared plus the base squared. That will be equal to D1 squared. And D1 will be square root of that. So this base is S11 minus X1. And the perpendicular is X2 minus S12. This is the perpendicular. So this is the distance, geometric distance of the received vector with the S1. Similarly, you can calculate the geometric distance between the received vector and S2. So that is D2. And then what you have to do, so you go on calculating these distances with all possible constellation points and then choose the one which has a minimum distance. So that is another way of detecting which particular waveform was transmitted. Okay. Now we'll just clear up a point or two about units. So far we have not said anything about what are the units of phi 1t, what are the units of S11 and so on. So let us clear that point up. So units of phi t. So the basis functions must satisfy the orthogonality condition, that is 0 to t phi 1t whole square dt is equal to 1. Now this on the right hand side is dimensionless. It does not have any units, but dt has the units of seconds, time, s. So therefore phi 1t squared must have the units of seconds minus 1 by second, so that it will cancel with this second and this will match with the right hand side which is dimensionless. So phi 1t squared must have units of 1 by second. So phi 1t squared. So phi 1t itself must have the unit of 1 upon under root of second. Similarly, let's calculate the units of coefficients. So units of S1t will be units of S11 into units of phi 1t. Now let's say S1t is a voltage waveform. Let's assume that. So the left hand side has units of volts. Now this is units of S11 which we want to find out, multiplied by units of phi 1t which is s raised to minus half. Therefore units of S11 is equal to V into s raised to half. So if S11 has units of V into s raised to half, then squaring it will yield V squared into s, which perfectly matches the required unit for energy. So you take any coefficient and square it, then the squared value of the coefficient will have the units of energy. It's important to understand this. So let us do this calculation. Energy of S1t can be calculated in time domain like this: 0 to t S1t whole square dt. Remember, we are doing normalized calculation. That is why although S1t is a voltage, we don't see any resistance here, because we are always assuming for normalized calculation that resistance is equal to 1 ohm. So E is equal to S1t square dt. So energy can be calculated in terms of the signal, which is a function of time. What we want to do is to do a little derivation which will tell us an alternative way of calculating the energy in terms of coefficients. So let us substitute for S1t, so that is S11 phi1t plus S12 phi2t whole square dt. You expand this and it's easy to see, this can be verified by the students, that this turns out to be S11 squared plus S12 squared. Alright, so in this session we have defined what orthonormal functions are. We have seen how do we generate the signaling waveforms by using orthonormal functions. We have seen how do we generate these signals, and we have seen how do we detect the signals. We have looked at the dimensions of various quantities, and finally we have seen two ways of calculating energy of the signal, one in the time domain and other by using the coefficients. And that's all in this particular session.